The story starts in 2017. At that point, I was an assistant professor 2 years into my academic career, and we had published a string of papers using palladium to perform difunctionalization of various alkene substrates. At that time, I had an intrepid graduate student, Joe DeRosa, who now is an assistant professor at Boston University, who started dabbling with nickel and showing that it could do some interesting transformations that palladium struggled with. At that time, I was also directed to the graph shown on this slide by my treasured collaborator, Martin Eastgate, who politely pointed out that while palladium was great and widely used in many companies, including his own, for catalytic coupling reactions that stitch together the C-C and C heteroatom bonds found in pharmaceuticals, agrochemicals, and the like, there were both cost and sustainability drivers to thinking about other transition metals that might mediate similar reactions. Not only is the price of so-called base metals such as copper, nickel, and cobalt so low compared to the precious metals that you can't even see it on the y-axis of this graph. But equally important, there is major price volatility that reflects a few factors, including geopolitical factors, including the fact that chemical industry end users do not occupy a large enough fraction of use cases to really control price, that this was a major issue for pharmaceutical manufacturing that relied on these precious metals. From a sustainability perspective, nickel is not only much, much more abundant on Earth's crust, but also its harvesting generates far less CO2. The problem that has held up widespread adoption of nickel for catalytic coupling reactions in the pharmaceutical industry is that its mechanism, the mechanism by which it promotes such CC and C-heteroatom couplings, remains poorly understood, and the pre-catalysts that are often used are not always reliable. And as a testament to this, a different industry collaborator had conveyed to me that they have lost millions of dollars in batches of precursors that have gone awry with failed nickel-catalyzed couplings. I mentioned Martin Eastgate's name before, and he played a very important role, not only in pointing me towards this direction and pointing our group towards this direction, but also supporting an internship for a graduate student in my lab, Van Tran, who traveled to BMS and worked under the mentorship of Steve Wisniewski, who's here in the audience, to try to understand mechanistic details of nickel as it pertains to catalyst activation and initiation for these types of coupling reactions. From that very academic exercise, that very basic science exercise, arose a series of precatalysts whose stability, both in terms of thermal stability and stability with respect to air and moisture, vastly exceeds the state-of-the-art at the time for academic researchers, which is the complex shown here, nickel bis cyclooctadiene, nickel COD for short. It's a beautiful canary yellow solid, and academics love to use this precatalyst. They store it in their glove box freezer, they bring it out, they set up reactions, and they put it back in the glove box freezer. But there's a clear disconnect between this mode of operation and how one would operate in an industrial setting. And we found that by coordinating electron-deficient diene ligands, like the one shown here, duroquinone, you can vastly enhance nickel's stability while maintaining catalytic potency. The implications and impact of this finding are pronounced. Not only are we now able to escape the tyranny of glove box chemistry and the associated energy. That actually wasn't meant to be a joke, but I appreciate the laughter, and the associated energy usage. But now we're able to democratize nickel catalysis research and distribute this catalyst all around the world so that researchers, even those lacking the infrastructure required traditionally for using low-valent nickel, are now able to advance new modes of coupling. And this has been reflected in widespread adoption of this family of pre-catalysts in academia and in industry. I think it's not an exaggeration to say now every major pharmaceutical company in the United States, at least, has this family of pre-catalysts in their screening library. And true to, or echoing a point that Paul made in his introductory remarks, sometimes doing what's sustainable and what's aligned with green chemistry actually can have additive value. And we've not only found contexts like the one shown here, where nickel is able to recapitulate the reactivity seen with precious metals, but we have seen nickel actually outperform precious metals, like in the two examples shown here.